Hello everybody, good to see you all again, and welcome to the daily live stream. So as usual, we're going to have some fun talking about some different areas of math, some of which I don't yet know, well in the sense that I don't yet know what we're going to be talking about. If you're new to this daily live stream, the way that we run this is different from your usual math class. Instead of having a topic which I've already prepared, what I like to do is I like to take this as my own daily challenge, where I find out what things you're interested in, and I see if I can improvise some kind of a mini lesson to help make this understandable. I know from experience that a lot of the people who are attending this are taking Algebra 1 or Geometry, some are more advanced, and what I'll do is whatever question I get, I'll try to answer it in a way that everyone can understand, even if they're taking Algebra or Geometry. I see that we have some people here who have been at this live stream before, judging from the fact that they know that I went back to my original shirt. I can tell you it's because I'm the kind of person who doesn't like to think too much about what I'm wearing, so I have a very, very simple way of deciding what I wear. It's called, if the high temperature for the day is 60 degrees or higher, then I wear shorts and a short sleeve shirt. And if the high temperature of the day is under 60 degrees, then I wear a long sleeve shirt and long pants. And that makes life much, much, much easier. So what we're having right now is you're seeing me in the middle of spring. And during spring, we have very wide temperature fluctuations from day to day. That's what happened. Yes, Starflower says yesterday was the gray shirt. I do indeed have more different colors of short sleeve shirts than long sleeve shirts. That is true. Okay. Well, in that case, wow, so somebody said I would die if it was 60 degrees. I wonder if that person just happens to live in a place where they measure degrees in Celsius instead of in Fahrenheit. Because, 60 degrees in Celsius is quite a lot. What's 60 degrees in Celsius and Fahrenheit? Gee, does anyone know a good way to convert between Celsius and Fahrenheit? This is something that I'm kind of curious about. What do people usually do? I mean, there's Celsius and there's Fahrenheit, right? So what would you do if somebody told you 60 degrees Celsius? And you want to convert this into Fahrenheit. A lot. Someone says this is a lot in Fahrenheit. Somebody says 1.8. Okay, there was a 1.8 that came here. And there's a formula which says that somehow if you take the Celsius temperature times 1.8, which is this 9 over 5, and then plus 32, that's equal to the Fahrenheit temperature. Right? So that works, and we could do this. And what is that? So if I did this 9 over 5 times 60, that's 9 times 12, which is 108, plus 32, that's pretty hot. Fahrenheit temperature would have been 140. Yes, you might indeed die if you had that all the time. You could use Google, but that wouldn't be any fun. But I'm going to tell you something else. I don't know if anyone has heard of another way. There's another way to approximately figure out what the temperature is in Fahrenheit. Does anyone know what else you use? Like 9 over 5 is okay. 1.8 is a number you can multiply. But there's another rule that sometimes people use. And they use this rule if they want to save some time. Does anyone know what this is? It's not actually just taking 1.8 times the temperature and then plus 32. Yes, somebody said 2 times the Celsius plus 32. So now it is not true that that's equal to the Fahrenheit temperature. This is the actual Fahrenheit temperature. And the reason this one is because if it's 0 Celsius, then it's 32F. And if it's 100 Celsius, then it happens to be 212F. And that happens to match it perfectly. But this other formula, it's actually not 2 times c plus 32. The other formula people often use is 2 times c plus 30. The whole purpose of the other formula is to just very quickly get an answer. Okay? And it's not necessarily right. It's just approximately. In fact, it gets more and more wrong when the temperature is too high. So for example, if I do this, I do 2 times 60, which is 120, plus 30, that's 150. On the other hand, I got approximately close. And the reason why, by the way, people like to use this 2c plus 30 is because it's really fast. I mean, if you wanted to try it on some other number, let's try it on some other number. Instead of 9 over 5c plus 32, let's do it for a number you're used to seeing. Some number like, I don't know, 17 degrees Celsius. That, by the way, is a number that is quite a reasonable temperature. The only reason I know this is because I spent a year living in England. I was in Cambridge for a year, and so I had to get used to Celsius degrees. 17 degrees Celsius I could live with. So if I want to know what this actually is, the Fahrenheit actually is 9 over 5 times 17 plus 32. Who likes to do this kind of calculation? Nobody. I don't like to do this kind of calculation. The number is terrible. Does anyone know an easy way to do this and get the answer? I'm kind of curious what you would do if you had to do this 17 times 9 over 5 plus 32. I know some people would type this into the Google, and I guess Google would answer that for you. Nobody, no me, no one wants to do this. You know what? Let me show you a way that I do this. It's actually an interesting arithmetic trick, and then maybe we'll talk about how it works. I use 1.8 times 17 plus 32, and I have a certain way of multiplying two numbers which are both in their teens. Here's what I do. I first take the 7 and add it to the 8, and that makes like 25. I want to tell you a way to multiply two numbers in your head, which are something like 18 times 17. What I do is I first add the 17 to the 8, add the 7 to the 8, that makes like 25. And then I say, there's going to be some other digit here. Then I say, just kidding. I actually want to put 56, 8 times 7. I want to put 56 on the end. And if I want to put 56 on the end, well, then it looks like this. But you can't write two 5s on top of each other. 5 plus 5 is 10. So that's a 0. And you carry, because it's 10, 306. Is that 18 times 17? I hope so. 18 times 17. In fact, this is a really nifty trick. I'll do the trick with another bunch of numbers. Here's another bunch of numbers I could just do this trick with. It's just kind of surprising that it works. If I do something like, let's say, I don't know, let's do 17 times 12. All I have to do here is take the 2 and add to the 17. That makes 19. Blank. And then I do the 2 times 7. It's 14. Put the 4 here, and when I carry the 1, that turns into 20. Oh, wrong answer? Did I do it wrong? 306. Well, I'm looking at the chat. It seems to be okay. Let me try another one. Let's try some more teens. Another teen. I don't know. 13 times 14. Okay, what do? I do the 4 plus the 13. That gives you 17. Blank. Then I do 3 times 4, which is 12. The 3 times 4 is 12. As I try to write the 12, oops, the 17 becomes an 18. It carries. It always works. Actually, as you get used to this, you can just do it really fast. Like you look at 18 times 17 and you say, so that's going to be like a 25 and like a 25 and a blank. And then I'm going to put a 56 on that. That's 306. So you're at 30.6 plus 32. Okay, so this is a nifty trick. Why does it work? Is it valid for any other number? Let's find out. You know, like, I'm glad you asked that question. In fact, the fun part is to find out like when these tricks are true, when they work. So let's just do some more things. I'm doing all these teens, by the way. I'm intentionally doing the teens. If I do like another teen, I don't know, 15 times 13, I made that up. What do? 3 plus 15 is 18. Put a blank. 5 times 3 is 15. Whoop. Bam. 195. Now, why does this work? It's not rocket science. Actually, all I'm doing is I'm just doing the normal way you multiply the numbers, except that I'm doing it in a way where I don't need to write as much stuff, and that makes it easier to do in your head. Oh, you have a 26, you have some other ones. We'll talk about other ones. But first, let's see why this works. Because if you're doing it the normal way, 15 times 13, okay, what do you actually do? So look, first I'll have the 3 times 5. That makes 15. So I'm going to do it the really normal way first, but I'll use some colors. 3 times 5 is 15 like that. Then I take the 3 times 1, and that's 3. I'm going to put the 3 in green. And then I'm going to do 1 times 5, 1 times 1. I get to put this down. What do you see has just happened? If you look at what I just did, oh no, I made a mistake. Thanks guys. I made a mistake. It's not, I can't put a 3 here. 3 times 1 is 3, but I have to carry the 1. This is wrong. That's not exactly a 3. That's in fact supposed to be a 4. But that 4 is that 1 plus the 3. So how can I write that? I guess I will write it like, oh, I'll just use another color, 4. But the important part about the 4 is that it got the carry from the 1, and otherwise it would be a 3. So in fact, if you look at this, if you look at what just happened, once I start to do the addition, I am in fact adding 3 to 15. I mean, I'm adding 4 to 15, but that's only because of the carry from this pinkish purple stuff. So that first bit that comes down here is in fact the 15 plus 3. So it's sort of like 18, except there's the carry of the 1, that's the carry of the 1, and then the 5. So this is why this trick works whenever you're multiplying teen by teen. If it's not teen by teen, it all breaks down. It actually just doesn't work. You see, because if I change this 1 into a 2, and it's like times 23, oh no, down here I don't write 15. I'd write 30. And if I wrote 30 here, what am I doing? I'm not actually going to have a nice answer. I mean, to be honest, you could make up your own trick that uses the 2 instead. But I'll say that usually you see these kind of teen times teen things more often, like what we just did here, like just converting 17 Celsius into Fahrenheit. And so it's very, very useful to be able to know multiplying teens in your head. Okay, fine, but let's finish. So this answer is, I think I saw some people type it. This is 62.6 degrees. Hopefully. I'm not sure if I got that right or wrong. You guys on the chat have to let me know. But my hope is that 17 degrees Celsius is 62.6 Fahrenheit. It actually does make sense to me as a human being who has lived both in the United States and in England, because I think they felt about the same. You know, like somehow I know what the 60 degrees feels like in the United States, and I also know what the 17 degrees Celsius feels like in England. Both of them feel like it's pretty comfortable, but a little bit on the chilly side, okay? But then there's another thing you can do. I wanted to compare this to the other way of doing a shortcut to approximate what the Fahrenheit is. The approximation would say Fahrenheit is approximately 2 times the number 17 plus 30. This, by the way, is very easy to do. I don't even need to write this multiplication. 2 times 17 is 34. Plus 30 equals 64. So that's not bad. Actually, it's pretty close. So, in fact, the reason why this 2 times 2 times Celsius plus 30 makes sense, does anyone know why if you use 2 times it, you should not add 32, but you should add something a little bit smaller? You know, like the real thing is this 1.8 times the Celsius plus 32. But if I just want an approximation, I'll go with, you know, don't times 1.8, times 2. But then I don't need to add 32 anymore. It's sort of rounded, and I should round down, not up. Because if I round up, it's like I got bigger on the 2 and bigger on the 32. So it makes sense. So it's like somehow this is a pretty good rule of thumb. So my advice to you is if anyone's ever telling you any Celsius temperatures, and if you live in the United States, for most temperatures that human beings will enjoy living in, this 2 times Celsius plus 30 gives you a good idea of how warm or cold it is. And then when you actually need to figure it out, if you ever find yourself converting like a pretty normal temperature, at least in England, a lot of the temperatures during the day, the high temperatures, were usually in the teens. Those are comfortable temperatures. Then you can just multiply with this teen trick, like 18 times something. Okay, well that little mini lesson came out of someone just saying that somehow 60 degrees feels like it might be too hot and they might die. I wonder what else we can do. This is always fun for me because now it's improvising time. What kind of questions do we have here? Wow. I see that. Let me see. I'm trying to think if I should go with that. Yeah. Okay. So somebody said, Andrew Chow asked, can you talk about the combinatorial game theory? I mean, I think you're sort of talking about game theory in general. And game theory is sort of like this question of what do people do to win games? So you look at the rules of the game and you try to figure out what might people do if they want to get the best for themselves, however that's defined. I'll explain this in an example that I'm dealing with right now. As you know, we launched this app called Novid, which is supposed to track whether or not anyone has self-reported that they are testing positive for COVID-19. And it's a voluntary self-report. And so this app hopefully is going to help reduce the spread of COVID-19 as people self-report. But oh no, what if somebody just decides they want to be an epic troll and just kind of press this self-report button just to annoy people? That would be terrible, right? So then what we need to do is we need to think about game theory. Game theory is to think, all right, from the point of view of that person who wants to be a troll, how do we make it so that they have the least ability to troll people? And furthermore, the way you do that is you would try to make it so it's actually no fun to troll people. And I'll tell you, after we thought deeply about this, the game theory is called, all right, so suppose we put in some rules, how would that person go? More sophisticated game theory is when there are two players and somehow each player does some moves. And you try to say, well, if this person did this, then what should that person do? If this person's strategy is this, what response should the other person have? We're sort of always positioning ourselves that way. And so what we ended up doing is we ended up saying, we'll just make it so that you can't report anyone until you have installed the app for 7 days. And then the people that you'll directly impact will be the people that you're around that for at least half an hour during those 7 days. At which point, it's no fun to use this to troll people. Number one, it takes forever. You only get to troll one person every 7 days. There are not troll one person every 7 days. You only get to troll once every 7 days. And there are other ways to troll people, like with other things, right? It's just called, you need to be the least attractive way to troll people. It's sort of like if you're running away from the bear. You don't need to run faster than the bear. You just need to not be the slowest person who's running from the bear. But the same principle is here, that these are all game theory ideas. And so what we eventually decided to do is we said, great, let's put a 7-day thing on it. And at that point, it's really not much fun. It's like, oh, what if you got 7 devices? You could, and that'd be pretty expensive too. It's like, the point is like, you want to make it so that if someone wants to troll, there are easier ways to troll with other things than messing around with something that's valuable. And so it's like, okay, it takes 7 days. But it's even worse, because then what we also do is we don't actually immediately report that. It's like if you press the button, there's no guarantee that that immediately sends a report out. Because actually what we are doing is we're able to find out who is near who, where who means I have no idea who you are, but like some random user number 56 is near random user number 6,000,000,002. I don't know who those actually are. I don't even know what country they're in. On the other hand, if somehow you report and no one else around you reports, that might be bogus. Do you know what I mean? What I'm trying to say is like somehow it's an infectious disease. How could it be that this infectious disease suddenly just dropped into one place all of a sudden? So what I'm trying to explain is that at that point, the person who's trolling doesn't even know for sure that the trolling is going to work. In fact, the trolling is going to be circumvented. And yes, Yi-Tong Lee says, don't be a troll, people. You are totally right. Troll is no fun. And anyway, especially because there might be clever people on the other side screwing around with the trolls. Trolling the trolls, so to speak. Because you see, if at that point the troll doesn't even know that pressing the button is going to troll anyone, then what's the point, right? So that's an example of game theory. And eventually, I do believe that if you think a lot about mathematics, you will be much, much better at thinking about game theory, much, much better about reasoning about what you should do. Actually, I can tell you another story. So last night, I was very deeply analyzing other protocols, other algorithms, other systems that people have come up with and proposed for doing what we're doing, which is called this anonymous contact tracing. I was looking very deeply at what other people were trying to do in this space. And when you do that, it's really helpful to be able to think in the game theory way of how would an attacker, a determined attacker, how could they break this encryption? Or how could they try to do something which uses information that they have watched or observed to find out more than they're supposed to have? And all of these ideas of cryptography and cryptanalysis are very, very deeply related to game theory. Okay, so it's related to stuff I've been thinking about, actually. More questions. What do we have here? Rong Hong Lin asks, what happens if somebody tests positive before 7 days? Well, in the first time when we release our app, unfortunately we won't be able to do anything with that because we're trying to minimize, due to the game theory, we're trying to minimize trolling. But after enough people in the world install the app, then we'll just say, yeah, you can install it, it's fine. And we'll be able to figure out who might be bogus. Maybe not definitely, but we'll have a good sense of who might be bogus. And so it's just a matter of you need to have enough information about the anonymous network in order to make your things smarter. Okay. Yes, Paperboy says you should troll the troll, the troll the troll. Wait a second. So there's like, this is the important thing here, by the way, is about evenness and oddness. That's a word called parity. Like some numbers are even and odd. So when I see troll, the troll, the troll, the troll, it's like it's got 4 of them. So if there's 4 of them, you're a good person. Because like 0 of them, then you're obviously good. 1 of them, you're a troll. If you troll trolls, actually, I don't know if I should say that makes you a good person, but I just mean that you're on the side that is at least trolling trolls. Unfortunately, 2 wrongs do not actually make a right, so I don't really recommend that. But no matter what, don't troll the troll the troll. Like then that's like definitely bad, right? So it's one of these things. It's like 2 wrongs don't definitely make a right. 2 wrongs are not necessarily a right, but 3 wrongs are a wrong. Maybe I just made that up, but it seems to make sense. And then like 4 wrongs, troll the troll, the troll, the troll. I'm not really sure if that's good or bad, but troll the troll, the troll, the troll, the troll. Now that's definitely bad. Okay, I think we've done enough about parity. But parity is a fun thing of like the evenness and oddness. Okay, what else can we do? Somebody said yes. Oh, Aaron Peng said he shouted. Yeah, occasionally I get excited. To be perfectly honest, usually I like to give talks like holding a microphone. I really miss going out in public and giving these kinds of public talks. Usually I do the microphone, and whenever we're doing the mic setup in a room, usually I have to tell the sound person, please be careful. When I get excited, I can get really, really loud, like much louder than most people normally are with these microphones. But it's really sad that we don't get to go out and do those things anymore. That's why we made the app. Okay. Oh, that's cool. Here's a question. Pompon Wang asks, how do you find the degree angle without a protractor? That's a neat question. I wonder if I can tackle that. What would I do? So I'm going to draw a degree angle. I don't know. Here, it's a degree angle. Okay, what's this degree angle? How would I find this out without a protractor? Here's what I would do. We are used to talking about degrees, where when we say the degree measure of an angle, we say it in something like, I don't know, we say like 37 degrees. We'll say stuff like that. Okay? Actually, the 37 degrees is a really funny concept anyway. It's 37 out of 360, right? Like a degree is out of 360. So let's just talk about it as a fraction. You see, because the reason it's a nice round number is for no other reason than the fact that we chose 360 degrees to be a whole circle. And we chose 360 degrees to be a whole circle because that's easy to divide into pieces. I see that Rong Hong Lin says, you could just trace a protractor. You could, but that wouldn't be fun. So let's try this, okay? So if I have a 37 degrees, really it's not, I'm sorry, I don't have 37 degrees. This is definitely not 37 degrees. It looks pretty big. It looks more than 45 degrees. It looks more than 45. But I'm going to think about it as fractions, okay? I'm not going to think about 37 degrees. I'm going to think about what if we wanted to find out as the fraction of the whole. All right? At some point later in life, you're going to learn about something called radians, where you go and say that the whole circle around is 2 pi radians, which is not even nice to divide at all. But I'll talk about them as fractions, okay? Let's talk about them as fractions. We could use trig, but where's my trig? I don't have anything that I can look at. Oh, actually, I could. You're right. You could use trig. You could go and measure some lengths and then divide them and then take some inverse trigonometric functions. You could. But I'm going to give this lesson in a way that it works for somehow anyone taking algebra or geometry. The trick is to not think of writing things in decimals. You know, like what's 37 over 360? I don't know. It's something ugly. But since 37 is very close to 36, this should be close to 36 over 360, which would be 0.1. And it's a little bit bigger, so I'll tell you that much about the fraction. It's 0.1 and something. Now, what I want to do is I want to not tell you what fraction this is as a decimal in base 10. You see, we're used to base 10. Base 10 is where I write 0.1 something, or 0.2 something, or 0.3 something, or whatever. Thank you. Actually, I'm going to use what Eileen said. She said it's 0.102, which I'll keep that, okay? And the reason I want to write that down is because this means 1/10 plus 0 over 100 plus my head. I guess I'll write smaller. Plus 2 over 1,000. Maybe not my head. Okay, that's good. It's like right above my hair. But like this is what we have. And then plus more stuff, okay? Plus more stuff. But you see, that's because we use base 10. If we're using base 10, we think of everything with the fractions, and the fractions are like powers of 10. Here's what I would do if I didn't have a protractor. I would figure out the degree measure in base 2, like this. So first what I would do is I would say, here's a line, all right? Let's go and continue the line. Zoop. So I just continued the line. Now the question is the angle I'm interested in, is it less than this much? Or is it more than that much? Well, it's less. Since it's less than the half circle, my angle as a fraction in base 2 is, I would say it starts with plus 0 over 2. So here I'm going to tell you what my degree measure is. So my measure as a fraction of a full rotation equals, I start with 0 over 2 because I don't want to take half. I don't want to start with half. Okay, fine. I know that. Next thing, I need to go and figure out what is a quarter. And, well, I should draw a more vertical line than that. Let's just draw a line straight up. How would you draw a line straight up? Well, there is a way to do that using what's called a compass. I don't know if you saw a compass before. A compass is where you have like a pen on one side and like a spike on the other side. Please don't poke anyone with a spike. You kind of do this. Has anyone seen something like this before? You can make this compass thing. Yeah, you make this compass. So here's what you do. You grab your compass and you stick the point, the pokey point, right there at that intersection. And then you kind of sweep the compass. Okay, you sweep the compass from here all the way around to there. So if I did that, I would poke the point right here. I would sweep here, and I'd sweep all the way around to probably around here. No, that looked like it was too far. Probably around to here. Does this make sense to people? I'd like tick that and tick that by sticking the compass inside and going around. All right? And then what you do, poke the poke point. Yes, yeah, you know the poke point, right? In this compass, the compass has a spiky point and it has a pencil or a pen. So you put these here, okay? They're used for drawing circles. They're items for drawing circles, right? Oh, a compass is not just the thing that tells you which way is north. The compass is this thing which has like a pencil and like a pointy thing, like a pointy thing for really jamming into your paper, and it makes a hole. Okay, great. So I did these two. Then the next thing I'll do is I'll just put I'll put the pokey point in here, and I'll make the other part kind of sweep across this way. So I'm going to put the pokey point in here, and I'll make a sweep that kind of goes through this way. By the way, that should look like part of a circle, for which the center of the circle is here. And then I go here, and I do the same thing, but I sweep that way. And look, where they cross is going to perfectly give me a way that I should draw an up and down. That's actually true by symmetry. So then what I'll do is I'll say, great, let's draw this line right through. Next I ask, is my angle that I'm wondering about, is this angle bigger or less than what I have there? Well, it's less. Since it's less, I don't want to add a quarter. You see, I did a 0 over 2 already. If it was over there, if my angle was over there, I'd add a quarter because I want to at least pick up this quarter and then continue on. But I don't have that. So since I don't have that, I'll add a 0 over 4. And it'll get more interesting soon. When I say more interesting, what I mean is we'll have more numbers to add soon. So now I have that drawn. Let's do the same thing again. You grab the poke point, you poke it here, and then you sweep it. You sweep it like, well, you sweep it sort of like this, around. So the poke point goes here, you sweep here, and also you sweep here. Those were supposed to look like they were the same distance away from each other. Okay, we got these two. Now, once you got these two, we're going to do the same trick again. We stick the poke point in here, and then we do a sweep that's kind of going over this way, like a part of a circle. And then you put the poke point there, and you do a sweep that's like this way. So I put the poking point right here. I do a sweep. And the sweep happens to be like making part of a circle. I don't know, maybe something like this. And then I put the poke point there, and I make another sweep, which makes another part of a circle. I'm not sure if I drew these right. These don't look very circular. Maybe I should have made this one longer. And then maybe the other circle, something like this. Okay? But the important thing is I can now draw this line that's through there. And what I'm doing is I'm very consistently cutting the angle in half every time. So now since I drew that, now here's a question. I wrote 0 over 2 plus 1 over 4. What should I write next? This is interesting. It's not 0 over 8. You see now what I say, is that the angle that I'm wondering about is here. And that goes beyond. That goes beyond this line right here. Since it goes beyond this line right here, I'm basically cutting in half every time, right? What I already know is I know that my angle is going to be more than 1/8. So I'll in fact add 1/8. Okay, so now I'm already here. And I know my angle is going to be 1/8 plus something. So let me erase part of the green. And I'll tell you, I'm now just curious, what is this angle, the green thing? If only I could figure out that green angle, I would add that onwards. Does this make sense to people? Because 1/8 went up to here. And then now I need to add something more. And all you do is you just keep doing this procedure over and over and over again. You can keep cutting it. As you keep cutting it, you'll either add plus 1/16 or plus 0/16. In this particular picture, I'm not sure. It sort of looks like it's plus 0/16. But it also looks like it's pretty close. But I don't know if this makes sense already to people. It's actually quite simple. You make your poke point. You poke now in the intersection as usual. But this time you poke and you sweep like this and like this. Right? So I've swept out this way. And then what I'm going to do is I now take the poke point and stick it into here and do a sweep and stick it into here and do another sweep. And when I do these two sweeps, it's actually going to come pretty darn close to that line. If I was going to draw it, my guess is it would be something like this. Probably be slightly off. Something like this. But once you draw something like that, then you say, okay, then the next thing should be plus 0/16. And once you're there, then as you keep going, you see you'll keep cutting in half, cutting in half, cutting it in half. In fact, I can tell you, the next one you'll do a plus 1/32. The reason it'll be a plus 1/32 is because I can already see that what's left over, you should add at least half of it. You're trying to get to this white line. Okay, so I hope that this is useful. I hope that you can see how this thing worked. What we're doing is we're figuring out all of the digits of what fraction is it out of a full rotation in base 2. That's what we've just done. And so you don't even need a protractor. If you're willing to just figure these things out in base 2, where you add up all these fractions, and anyway you'll approximate at the end, then you can do a measure of an angle using only a compass, which is actually really cool. I actually didn't even think about that until after you asked me that question. In fact, I just came up with this right now. So I guess it seems reasonable. It seems reasonable. I can do it. If you just gave me the compass, I could go and figure out an approximation to the angle. So I'm satisfied with this answer. And I'll also say that this is in fact just about as good as you can do with a protractor, because I'm going to break it to you. Unfortunately, there is no angle in the world that is exactly what you wanted it to be. It's always approximate anyway. All of our measurements are approximate. Like it might be off by nanometers. How in the world can I make sure that I have exactly the right number of atoms in something? You know what I mean? So it's always going to be slightly off anyway. And so if you don't get it, roughly speaking, what I'm saying just keep cutting things in half. It's sort of like this. Have you ever played this game before called Guess a Number, where I say, I've got a number between 1 and 100. Guess the number. And then the other person goes like 50. And I go, oh, it's smaller than 50. And then they go 25. And I say, oh, it's smaller than 25. Then they say 12. And I say, oh, it's bigger than 12. By the way, that's exactly what we're doing here. That's exactly what we're doing here. What we're doing is we're first saying, is it more or less than half? If it's less than half, put a 0/2. If it's more than half, add a half already. Then it's like, okay, so it's less than half. Then how does it compare to a quarter? So that's basically what we're doing here. Okay, it's a guess the number game, just with a compass, and you can find the degree measure of any angle. All right, I'm going to take a sip of water while I try to figure out what question to answer next. Oh, Michael Wu has an interesting question. I also have one good eye and one bad eye. That's pretty neat. So I'm not alone. It's very interesting. And he said, how many hours did you do math for when you were a toddler or child? Thanks, I often look up to you. Well, thank you very much. When I was a toddler or child, I don't really know. My mom would know. I don't really remember. I don't know if it was like a huge number of hours. I'm not even really sure what I did as a toddler or a child with that kind of math. maybe one, something like that. Maybe, but I did a lot of reading. So maybe one, maybe two, but I did a whole lot of reading. And so I think the important thing about learning is that there are lots of different things that you can learn. Actually, as a toddler or a child, the different things that you play with can also teach you lots of stuff. I was doing a lot of stuff with Legos. You know, you're asking about like really young age, right? So I liked building stuff. And, you know, later in life, I spent much, much more time doing math, but that was also related to having some more interesting questions to do. So sort of like how, you know, you guys are asking me these questions, and I'm very intentionally choosing the questions that are, you know, interesting. Okay, I see an interesting question from Rong Hong Lin. Why do you like people? Why not? People are really interesting. I mean, I just think that people are really interesting. That somehow when you talk to a person, it's just like a real person. I don't know. It's like, I don't know. They're video games, right? Like, so there's some video games where you can play against the artificial intelligence or play against the computer. Those are not interesting. The computer is really boring. I don't know if anyone else feels this way, but like the reason why these multiplayer games are so popular is because you get to play against a real person. And the real person is like clever or dumb, either which, but somehow they are a real person. And that's actually interesting. I am interesting, yay, says Itang Li. Yes, you are. You are interesting. Like, real people are interesting. And so I guess that's why I liked it. I think that sometimes people don't like talking to people as much because they might be shy. I think that that's quite normal. At the beginning, it's like, oh, what if I say something? What will they think about me? If you overcome the shyness by just trying, then after a while, it's not about being shy. It's just being fun. I think also for me in my life, I changed schools a few times. So this is a personal history thing. You know, I went to a school and then my family moved somewhere and we went to a different school. So I went to different places in my life. At some point I went to summer camps. At some point I went to college and so on. And every time I went to a different place, I would just go and say, well, you know, people here don't really have any expectation about who I am. They don't know who I am. So I don't necessarily need to have the same kind of reputation or the same kind of baggage or expectations as when I was at the last place. So I'll just go and say, let's try personality version number 2 or personality version number 3. Or it's just very actively thinking, what can I do to be more effective about dealing with other people? And after a while, if you go and actually try to learn from each of these times, after a while it works out pretty well. But yeah, I like people because it's interesting. And I'll tell you another fun story, okay? So it's about people. Recently, I also see people asking about this Novid app coming out. You know, the biggest issue I'm having right now is that the Google Play Store is not accepting it because Google Play is blocking all of the apps that have anything to do with COVID-19. It's very, very sad. It's like the app is done. And what I'm doing right now is I'm writing to the city of Pittsburgh. I'm writing to hospitals. I'm just trying to contact people to try to help get some support to say, hey, this is a good idea. But as I was doing this, and I was just I asked on the internet to like everyone that I know, and all these people come through the woodwork. It's like the people that I went to middle school with, the people I went to high school with. It's very good to be like, you know, find that people are interesting. I'll just tell you, to me, the fact that last night I got so many interesting people connecting back and helping. These are people who I haven't seen for 20 years. But somehow, if you leave a good impression and you are a good citizen when you are in middle school or high school, maybe at some point, 20 or 30 years later, you find yourself releasing something and you say, oh my gosh, I wish I knew someone who was a doctor. Well, there might be a few. You might know a few doctors, and they might even give you a hand, right? Or they might be people who have become complete experts at programming smartphones. Like this is just like all these people who are coming through the woodwork. So it's just like, I'll just tell you, like this thing about people, it's a real useful thing. If you just learn math, it's okay, you know, you can do math problems, but then you'll be stuck your whole life just being able to do math problems. If you figure out the people aspect, at some point when you have something that you need to do and you run into a roadblock, you can actually get the help that you need, because nobody can do everything. I can't. Okay. More questions. Oh, Meet Movalia says, do you know IIT JEE? So, IIT JEE. So you see, when I was growing up, I had no idea. I had no idea what these things were. Like, what in the world could an IIT JEE mean? Clearly, it's an ITG. As far as I was concerned, I was like, I have no idea what this is. ITG. What's an ITG? Well, it turns out that this is extremely important. It's not just an ITG. It's sort of like if you were like not from America and you go and ask, what in the world is a SAT? Why do you sat? Yes, I know I sat for a test. I sat for the SAT. Well, I mean, it's a name. The SAT is actually a SAT, right? Or like some people will be like, the USAMO. What's a USAMO? What's a USAMO anyway? So these are all like content. These are all like very very important in some degree types of exams or things that are useful. Like the SAT is somehow the American college entrance exam. And goodness gracious, I don't know how they're going to give the SAT now, given that somehow we can't go to a testing center. Actually, I never thought about that. I don't even know what's going on with the SAT anymore. The USAMO is the USA Mathematical Olympiad, and that's where you sit in a room for 9 hours and do math problems. But the IIT JEE, yes, I learned about that after I started going all around the world. And I learned that the IIT JEE is extremely important. It's the Indian Institute of Technology joint entrance exam. So IIT is one of the most prestigious institutions it's a set of institutions in the country of India, Indian Institute of Technology. A lot of amazing people come out of that. And the JEE is a joint entrance exam because you, I guess, take the IIT JEE, and based on your scores, it's the joint entrance exam that has some scores sent to all of the Indian Institute of Technologies. So I understand that this is a very important thing that many people care about. Also, it's highly, highly competitive. So what do I know about this? I know that there are people who know how to do amazing integrals. So on every test, they ask different kinds of questions. On the USAMO, every question is like, prove this, and it'll be some complicated statement about geometry, or like some complicated statement about number theory. The SAT will ask you something like, maybe something with algebra, okay? The IIT JEE, it'll have all these crazy integrals, like weird integrals where, maybe I know how to do this one, maybe. I mean, I think this is like an easy one. To me, that one I think is a very easy one. I hope. Is anyone here in calculus? I think this one's actually arctan. But maybe I'm wrong. Maybe I'm wrong. I haven't done this in forever. But in any case, I see, yes, JEE integrals. Oh, yes. Somebody is commenting they have taken the SAT, but the JEE integrals are just like, oh my gosh, right? Like the JEE integral is not this one. It's some ridiculous thing. Oh, good. Arctan was right. Then I got that one right. But like, there's ridiculous stuff. And what in the world is the answer? You have to be very clever with these like U substitutions. There are all these tricks. In fact, I teach at Carnegie Mellon University, where there are students who come from all over the world to our university. And there's one class I teach. It's called the Putnam Mathematical Competition class. It's the one which people do really, really, really hard problems in. And every time, if there's some ridiculous integral, it's that student who's from India, and she just somehow she nails it. So there's this student who attends my super advanced class at Carnegie Mellon. I teach many different levels of this. One of them is the super advanced level. And if she's in the audience, and if it's a crazy integral, bam, she gets it, and it's over. So I'll say my observation of the IIT JEE is you guys seem to be pretty darn good at doing really complicated integrals. Yeah, I mean, it's interesting stuff. More questions. Screams in confusion. Yes, this is a high school topic, so don't worry. We're going to move on. Huh. Oh, interesting. Oh, there's a comment about the apps. Athena Wu said, there were a lot of fake apps that used to be on the App Store until Google banned them, though. Absolutely, there were. And that's why it was actually very good that Google was controlling what things go into the App Store. We need to make sure we don't get fake things. Let's see. Looking at all of these different sources of questions to decide what to answer. So Proper Pickle asks, what is the pigeonhole principle? The pigeonhole principle. I think I can tell you an example of the pigeonhole principle, which, let me see if this will work. Yeah, I think this will work. So, and this is related to things I've been thinking about lately. Hey, does anyone know how many digits there are in a United States phone number? How many digits are in a USA phone number? Does anyone know? Well, I guess we could write it down. 10, is it? So it's like the 1 in the front doesn't count, but it might be something like, 5, 5, 5, 1, 2, 3, 4, 5, 6, 7. So there are 10 digits. Now, in the US phone numbers, the first 3 digits are kind of important. the first 3 digits are what's called the area code, because depending on where you live, they somehow used to be. Now with cell phones, you can have an area code anywhere you want. But before cell phones, actually these 555 thing would mean it was this particular part of the United States. And that was because as someone was dialing a number, if you started to dial something, it would have to route the call to that particular area of the country, and then it would continue from there. 555, I believe, has a funny story where I think 555, I might have this wrong, maybe someone in the audience can correct me, but I seem to remember 555 is the bogus area code, where 555 is actually not any real area code at all. Please correct me if I'm wrong. It could very well be that I'm wrong. But there is one particular area code which is not real, but it's used in all the movies. And the reason why it's used in all the movies is so that if anyone, like the worst thing that could ever happen, by the way, is if there's a really, really popular movie and the phone number of one of the main characters happens to be your phone number, like your real phone number. That would be the worst thing ever. Because then when people are watching the movie, some people might be like, hey, let me dial this number and see if anyone's there. And you just get all these people calling you. So I believe that in the movies, they really try to make sure that whatever number that they use is not actually a real one. Somebody says that I'm not quite right. So in that case, I'm not sure which is the bogus one. There's one bogus one. 555 is the area code of Iowa. Oh no, then I'm wrong. Okay, so there's one other one. So let's not put 555. Let's say there's another area code out there. There's some area code which happens to be not legit. Okay, so 555 is not legit. Interesting. So maybe it was something else that was there. But anyway, hey, you know what? We said it's Iowa. So we can put 555 here anyway. 555 is the area of Iowa, area code of Iowa. So that's what you dial. But then there's also these 7 digits afterwards. And as you can see, there are plenty of times when I'm wrong too. And that's why I like to do these things where there's all of these people here. Oh yes, 911 is not an area code. Actually, does anyone know why 911 is not an area code? Well, actually, 911 is not a good example. 911, in theory, it could be an area code. The thing that's not possible is it's not possible to have a 911 here. You can't have a 911 here. And the reason is because, so different people. Yeah, 911 is the police. It's because when you start dialing a number, I don't know if it's still this way in the phones that you guys use, but if you use like a landline, the thing that you plug in the wall, if you just dial 7 digits and you don't dial that area code and you don't put a 1 in front, it just tries to dial. And if you dial 911, it's just over right away. In fact, phones are really interesting. Phones use what's called prefix dialing. The moment that what you have dialed is a legit thing to dial, it dials. Right? It's not just that 911 is short. It's just that somehow the phones know if you type 911 and don't type anything else, it goes to 911. And if you type 911 and keep typing stuff, it still goes to 911. But anyway, why are there 7 things here? Why not in the city? Just have like, this is too long. I don't want to use 7 numbers. I'd rather just use like 4 numbers for my city. Okay? I have a new idea. These phone numbers are just too long. Forget it. New phone number. I want to go back to Iowa. What does Iowa look like? Is this Iowa? I don't know if I have it backwards. Iowa to me is like either this way or the other way around. I forgot which one it is. But there's like one side is a little bump and the other side is more flattish. So we got this thing, and if this happened to be Iowa, what you do is a new idea. Forget about that. Let's just go with 555, and I have a new format for phone numbers. I just want all my phone numbers in the entire state of Iowa to just be like 4 digits. Like 4621. Wouldn't this be better? Let's just have all of the phone numbers in Iowa be 555 and 4-digit number. Why is this a bad idea? Amy Fan says not enough. That's the problem. That's called the pigeonhole principle. The pigeonhole principle is just the concept of not enough. Because if I go and say 555 is Iowa, how many numbers can I have anyway? The number of options. If I only have 4 digits to play with, how many different options could I make? Well, at most, there are 10 choices for the first one, 10 choices for the second one, 10 choices for the third one, 10 choices for the fourth one. It's equal to 10 to the power 4. There are 10 choices for each of those digits. And it's like 10 choices for the first times 10 choices for the second times 10 choices for the third times 10 choices to the fourth, for the fourth, which is only 10,000. Unfortunately, there are more than 10,000 households in Iowa. So that's why it doesn't work. So in fact, as you think about all of this stuff, you start to understand like why there are certain numbers of digits. Look at that one. Look, how many could you have with the normal thing, with like 7 digits? if you can have 7 digits over there, let's get rid of the X sign. Actually, the X sign should go over this bogus thing over here. This is bogus. So that's bogus now. But if I use that blue one over there, that option, the number of options you can have is 10 to the power 7. Number of options is 10 to the power 7, which is 10 million. Surely that should be enough, right? That seems quite reasonable. What does bogus mean? Oh, bogus means like wrong, I guess. I don't really know how to define that. I guess when I say bogus, I usually mean wrong and like really very wrong. I guess that's what I usually mean when I say bogus. It's just like very, very wrong. But okay, so it's 10 million over here. It's a lot. Sounds like enough for anything, right? Well, not quite. How many people are annoyed when you like pick up your phone and the person says, "Oh, sorry, wrong number"? Has anyone ever gotten a wrong number call before? You know, you the ring, 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 and you go pick it up and, wrong number. Well, you see, wrong number happens more often if almost all the numbers are used. Because, you know, as you're typing, it's very easy to just like mess up the number. So in fact, what you really want is you don't even want to use all 10 million. If you used all 10 million, you just keep, like anytime anyone pressed the wrong number, someone gets dialed. So you don't even want the full density. You don't want all of them to be there. So actually, this is only useful for a few million, you know, a couple million. And at that point, you get cities like New York City. And New York City, does anyone know how many people live in New York City? Anyone know? New York City, like the New York City area, it's me. Jacqueline So says, you live in New York City. New York City is like, it's a bunch of, it's a few million people in that area. It's probably, it's like, is it like 10 million ish? It's like, yeah, 8 million is what I'm used to thinking. So to me, 8 million, 10 million are in the same ballpark. So that's like the whole New York area. And by the way, that is a changing number. That's true. It is a changing number. But if you have about 10 million-ish people, 8 million people, that's why New York has multiple area codes. As some of you may know if you're in this chat, New York, the classic area code is 212. But there's also, is it like a 646 or something? I don't know if people here are from New York. Maybe you know, maybe you don't know. But I think there's a 212. I know there's a 212. And I think there's also like a 646. And somehow we need to have these different things only because of the pigeonhole principle. And that's, 201. Are you sure? I thought 201 was New Jersey. I'm not entirely sure. But anyway, doesn't matter. These are all things that I sort of pick up as I guess I travel around the world and kind of notice as you go to different places and have to call different people. 315. Okay, neat. Or is it 917? Maybe it's 9. I forgot already. Maybe 646 was somewhere in LA. I lost track because I used to live in all of these different places. Okay, cool. So what should we do next? So we're down to like about 5 minutes. I'm going to go and try to see if I can choose something to finish up. Oh, wow. Somebody asked, how about Shanghai? Yes. What are those Chinese phone numbers like? I'm trying to think of what my Chinese phone number is. I haven't been to China in a while, which is why now suddenly this, the number is coming back to me. So I'm thinking of my Chinese phone number, and I won't write down my Chinese phone number, but you know, the numbers in China are something like, you know, there's like a something, something, something. Okay, that's how many digits are in my Chinese phone number. So when I go and figure this out, like that's a lot of numbers. Wow. Yes, so my Chinese phone number has that many numbers inside, that many digits inside it. And if I go and count, it's got like 3 here, 3 here, 3 here, and then 2 more. So it looks like there are 10 to the power 11. Okay, and that might make sense. The reason that might make sense is, so 10 to the power 11 is pretty big, but the population of China is 10 to the power 9, roughly speaking. That's like a billion people. So if you're going to go all the way to 10 to the power 11, there's basically 100 times as many phone numbers possible as people, which is about right. Okay, cool. No vid, no name, no vid, no, yes, great. Yes, we're going to work as hard as we get there. Anjo says 13 in Shanghai. So indeed, my number is a Beijing number, so maybe that's the difference. Oh my gosh! So the world has lots of like places with lots and lots of people, and so one would expect that, for example, in China and in India, one might expect to have these very, very long numbers. But now you understand, and whenever you look at anything, it's like that's why some things have this many digits. That's why some things don't have this many digits. Other questions? Okay, let's finish with this one. This is a soft question. This, it's a fun question to finish with. Rosie Hong asked, "What sparked an idea for you to give speeches around the world about math?" Just a second. Yeah, speeches around the world about math. Oh, thanks for asking that question. Um, it's fun. I mean, I like performing. I like talking to people. I love being able to try to make some difference in how a person's life is. So I thought it was fun. This actually started with something much simpler, though. My first time going around the world to give some kinds of speeches was with work that I was doing with Carnegie Mellon University. So as you know, I work as a professor at Carnegie Mellon University. And our university likes to look for really, really motivated and passionate and very smart students. And so I was going on trips to go to some of these high schools where students who were, I guess, really, really good at math and science would typically attend. And I would go to these high schools and give some talks. And it would be sort of like, this is a real Carnegie Mellon professor. It's a chance for anyone who wants to know a little bit more about my university would be able to talk to me. And so I did that at first. And that was fun. And after a while, I also became the national coach of the US Math Olympiad team. And then I thought, maybe I don't only want to go to those super specialized schools. Maybe I can go to more places and go to more cities. And that was also fun. And after a while, I guess I got a little bit of a reputation. And then people started to say, "Can you come to my city to give a talk?" And I said, well, I like that. I'll try that. And I got to kind of go to all these different cities all around the US, all around the world, to go to different math circles. You may have heard of these before. Some cities have things called math circles, which is where maybe a local math teacher or a parent or a math professor is doing a nice session every single week to talk to people about interesting math. And I'd often go as a guest speaker to these kinds of things. And it was fun. And then at some point in my life, I said, I wonder if I can go to places that are even farther than just the United States. And that's when I started going to China a lot. Up until the end of last year, I used to go to China every 2 months. That's actually why I have this particular phone number. But unfortunately, right now, it's not really that possible to travel internationally. Although not a long time ago, when I was traveling to China, that was because I had my own inspiration was I wanted to learn Chinese. And so the better way to do that was to just go to China and to give math talks in Chinese. And I figured that was the best way to learn because it was a language exchange. It was an exchange, right? Basically, I would give the talk in Chinese and there would be people forced to listen and give me feedback. But in return, they get to learn some interesting math. And so it was a good trade. So that's what I did. And I ultimately really, really miss that lifestyle. I think it's fun to get to see you guys face to face and to sort of see how much I can get people interested in math. I was also inspired by a colleague of mine, another math professor at Carnegie Mellon, whose objective is, if there's ever a student in front of him in the classroom, his objective is to convert that student, however skeptical that student is, convert them to think that math is actually cool. And I learned from him, and I learned that such things are possible. So I sort of take it as a sport to go around. Sometimes there are situations where maybe student doesn't really like math, maybe they were sort of forced to do math, maybe they were forced to watch my YouTube video or forced to come to watch me, and I'm like, that's okay. We're going to show that this is actually interesting, right? And then I'll take that as a challenge on myself to try to help whoever that was to see that, this is actually really, really, really interesting stuff. And then it can be your idea too to be really good. Okay. Great. Well, in that case, I see some requests to speak Chinese. I'll tell you the only reason I don't want to do that here is because I want to respect the international audience that we have in this YouTube live. If you want to see me speak Chinese, just search YouTube, and you can find some of these interviews of me in Chinese with other people. But out of respect for the audience that we have here, which is not all fluent in Chinese, I want to make sure that we are, as inclusive as possible. And with that, I'm going to say I unfortunately need to run. We have to continue to push our work on Novid as much as possible. But it's a pleasure to see you all again, and I wish you a good day. I hope that you have a good day, and I'll see you all tomorrow.